So today's notes, we're going to cover section 5.2 in our textbook, which is solving systems of linear equations using the method of substitution. Before we jump into our notes, I just want to remind us, Chapter 5 is going to cover 3 ways to solve a system of linear equations. In Section 5.1, we covered graphing, so that's one method we already know. So this is just another tool to find the same exact answer, but our tool today is going to be substitution. So like the problems we did yesterday, we found the answers by seeing where they intersect on a graph. We're going to find the same exact answers today, just using a different method. There is another method in our textbook, which we'll get to in the next video, so just know that there's a bunch of tools to accomplish the same task. So just to remind ourselves of what we've done, this is a system of linear equations because we can see that this is in slope-intercept form, and then we also see this thing below it is in standard form. So both of those are forms of lines, which means that we know they're going to form linear equations. So I have a picture of those. So in our first example, what we know, if we were going to solve it with the methods that we learned before, we'd graph the first line. So there's the first line. Here comes the second line, and we'd simply say, where do they touch? And in this method, our calculator is just kind of figuring that out for us. But we know that they touch at -4, -1. So from 5.1, if we did graphing, this system has a solution of -4, -1. So our goal today is to get the same answers for x and the same answer for y without looking at a graph. So our general outline today, what we're going to do is the goal of substitution. So I'm just looking at our notes here. The goal that we have for today is we want to use one of the equations in the system that's already there to help rewrite the second equation. So like for example here, I'm going to use equation number 1 to rewrite the second equation. Now what's important to note is the second equation right now has 2 different letters in it. It has x and it has y. The goal of substitution is after I use one of the equations to rewrite another one, there should only be one variable left. Because if there's one variable in one equation, I would be able to solve that. So this is a general outline of the steps. What we want to do is we want one equation to have one of the variables all by itself. Then what we're going to do is we're going to use that equation that has a variable by itself, substitute it into the other one, and then we'll have a new equation to solve. So what we notice here is equation number 1 has y all by itself. So what that means is wherever I see that symbol y, I could either call it y or I could replace it with this whole other expression here. So I'm just going to highlight that in like an orange color. So what we're going to do then, what our steps would say is step number 1 is actually already done for us. We have one of the equations that has a variable all by itself. So what we want to do then is we want to take our second equation, which I'm just rewriting. What the goal is, I've seen something called y. So instead of calling it y, I can call it something else. So I'm replacing y with an empty set of parentheses. And what can I call y? Well, if I'm not going to call it y, I can use this thing called -2x minus 9. Because y and -2x minus 9 are the same exact thing. So I've substituted the first equation into the second equation. So wherever I saw that variable that was all by itself, I plugged it in to the second equation using parentheses. And that's one of my biggest tips I want you to add to your notes, that we should substitute using parentheses. So what we can do now is let's just simplify this equation. So we can just keep this as 6x. We'll distribute our -5, so that's positive 10x. And then -5 times -9 is 45. So now we'll just collect some like terms. 16x plus 45 is equal to -19. So we can see we've accomplished the general goal of substitution. We wanted to take one of the equations, put it into the other one, and rewrite it so it only had one variable in it. So this new equation here, which we can call equation number 3, it's a new equation, it only has one variable. If there's one variable, I only need the one equation to solve it, so I can just start getting x alone. So -19 and -45 is -64, and I want to get x alone by undoing multiplying with division. So I get the x value is -4, which we thought it was from our graphical solution. So our final step is once we got the value of one of the variables, we should substitute that value back into one of the original equations to get the last variable. So it doesn't matter which original equation we'd use, but I found x, so I need y. And if I want to get y this equation tells me exactly what it is. It says y is this. So I am going to choose the first equation because it's easier to get the value of y than the second one. I'm just copying it down. So wherever I see an x, I'm going to substitute using parentheses, and we think the value of x was -4. So that means the y value, so -2 times -4 is 8. So the y value should be -1. So algebraically, we found our x value was -4 and the y value was -1. So we organize it into an ordered pair. And that's what we saw in a graph. These two lines touch at the point -4, -1. So we've algebraically, or in other words, using substitution, found where these two lines touch. So that's the overall goal of substitution. We had an equation where a variable was alone. We took that variable and replaced it in the other equation, and then we were able to solve for one of the variables by itself. Once we got that value, we plugged it into an original to find the missing number. So the last examples that we have today, so let's kind of take a look at both of them. The way that these are different is we don't have a variable that's already all alone. So like we did here, equation number 1 was very easy for us because it was started with y by itself. So here, what the big idea is, we may need to rearrange equations to isolate a variable. Now just recall when I say isolate a variable, what that means, it should be the only thing or the only term on its side of the equal sign, and there should be a 1 in front of it. So with that, like with this one, there isn't a variable that's all alone because the x's and the y's are on the same sides, and that would be our first thing that we'd need to fix. Now, it doesn't matter which equation you use to get a variable alone. We do just ask that you take a little time to preface or like predict which one would be the easiest. So like in this first equation, if I wanted to get y alone, I would just have to add x to both sides. That's a really easy step to do. So I am going to take this first equation, and I'm going to rewrite it to get y alone. So I'm just going to copy it again. So -x plus y is equal to 3. So if I want to get y alone on its side of the equal, I want to undo a -x with a plus x on both sides. So I get y is equal to 3 plus x. So now I have y all by itself. So wherever I see this symbol y, like I see it right there, I can replace it with these other symbols, 3 plus x. So once I isolated a variable in the first equation, or in one of the equations, I'm going to plug it into the other one. So since I isolated in the first equation, I have to plug it in to the second equation. Now remember, wherever I see that symbol y, or wherever I see the symbol for what I isolated, I'm going to replace it with a set of parentheses, and instead of calling it y, I can now call it 3 plus x. So I just need to simplify this equation. So there's a 1 here, so we're just distributing the 1. We can collect our like terms, 3 x's and another x, that's 4 x's. So now this equation, which is new, so I'll give it a new number, this equation only has one variable. If there's one variable, I can use one equation to get the answer. So we'll just start to get x alone by subtracting 3 from both sides and undoing multiplication with division. So we think x is -1. So our last step, once I know what x is, I need to take that value and substitute it back into one of the originals. Doesn't matter which original I choose, I'm just choosing to plug it into the first one. So I'm recopying the first one. I know what x is, so if I'm going to substitute for x, I always replace that symbol with an empty set of parentheses. I'm going to replace it with the value of -1. So the opposite of -1 is 1. And if I wanted to get y alone, I would simply just subtract the 1 from both sides. And I see that y is equal to 2. So we have an x and a y, so we organize it as an ordered pair. So we think these two lines touch at the point -1, 2. I do already have that prepared for us to check. So in our example here, here's our first line. Here's our second line. We do say they touch, and the point at which they touch is -1, 2. Now, just as a quick point of clarification, I happen to get y alone in the first equation. It'd be very easy to get y alone in the second equation too. You could, if you wanted to. Like if I started like this, I could easily just subtract 3 x's from both sides and get y alone in equation number 2 and plug y into equation number 1 then. So it doesn't matter what equation you're using to get alone, and it also doesn't matter what variable you're getting alone. So if I have -x plus y is equal to 3, I could rearrange this to see that y minus 3 is equal to x, and I could get x alone. It doesn't matter what variable you're getting alone, as long as one of them is alone, and you're plugging that into the other equation. So we'll do one more to summarize our work here. We have a system of linear equations. I recognize that because they're both in standard form, and we know standard form makes lines. Now with that, I'm noticing that none of the equations have a variable that's all by itself. But I do notice that in the second equation, the coefficient of y is already a 1. So I am going to choose to use the second equation to get y alone. So I'm going to rewrite it. Negative 6x plus 1y is equal to negative 7. So to get y alone, I would add 6x's to both sides. So y is equal to 6x minus 7. So I got that alone in equation number 2, which means I need to plug that back into equation number 1. So wherever I see this symbol of a y, I'm going to replace it with a big set of parentheses. So I'm going to take equation number 1 and rewrite it, but instead of y, big set of parentheses. And instead of actually calling it y, instead I can call y 6x minus 7. So replace that with 6x minus 7. And again, that's just because we got y alone, so y and 6x minus 7 are the same thing. So we'll distribute our 3 and collect like terms. So here we have one equation with one variable, so it's our new equation, so we'll call it equation number 3. So to get x alone here, I'll just add 21 to both sides. To get x alone, I'll divide by 20. And we can simplify that fraction. They're both divisible by 5. So x is 5/4. So once we know what x is, we take that x value and we plug it back into one of the original equations. It doesn't matter which one we plug it into, so I'm going to choose to plug it into equation number 1. So wherever I see an x, I'm going to replace that with a set of parentheses. And we think the x value is 5/4. So we'll multiply. 2 over 1 times 5 over 4 is 10 over 4. Now in this case here, I'm just going to subtract the fraction. So we get 3y is equal to 4 minus 10/4. Now you're welcome to get a common denominator there. I'm going to choose to actually just sweep the fractions away real quick by multiplying every term there by 4, because that's the common denominator. So this would turn into 12y equals 16, and then 10 times 4 divided by 4 would just be 10. So I'm going to simplify that. So when I divide by 12, I get y is equal to 6 over 12, which we should obviously simplify to 1/2. So we think our final answer, the x value, was 5/4, and the y value was 1/2. And it'd be okay to call those decimals if we want to as well. Either one would be fine. So we can check our work on a graph. I already have it prepared. These are the two lines. We do see that they touch at the point that we predicted. So our final thing that I want you to write down in your notes is, why do we need substitution? We need substitutions for things like this. We wouldn't be able to graph this by hand super accurately because they don't intersect at a nice point on the graph. They intersect at decimals and fractions, which are hard to estimate. So the only other thing I'd want us to add to our notes is substitution is a great method when we can't be exact with a graph. So that's our substitution method for solving systems of linear equations.